Afternoon from semiconductor now. Before that is all advanced medicine, more advanced medicine. So we'll still squeeze for time, and forgive me, I am heavily jet lagged, so I'll try to make as much stories as possible. So we are a semiconductor company. We are actually a chip manufacturer. We are a startup. I started 5 years ago, and now we have our product that is already sampling to customers. Means it is shipping in small quantities. So, but rather than telling about our company, I'll tell you a little bit about electronics history, and I will also try to tell you where the semiconductor is going. Of course, in India there has been a lot of noise, a lot of talk about semiconductor, and hopefully what I'm telling right now will be relevant. So first of all, I don't know how many of you know, some of you definitely know, that the computers started being a mechanical device. It was actually something that you will switch on and off, or a gear that you will turn. And from computer device, it became, the next thing that came in the world was called vacuum tube. A lot of you will remember, may even have in your homes, these radios that will make very deep sound. That the technology that worked underneath was called a vacuum tube. After that, the computers became what became analog computers. And now, of course, we have come to age where the computers became very big and then became very small, to the extent that whatever costed around $100 million, IBM, 1980s, cost you around a few $100s, that's in palm of your hand, called a smartphone today. Approximately same amount of compute power that used to be there. Now, important thing about these computers or these electronics or semiconductor is that semiconductor, I mean, all of these devices, whether you had the vacuum tube or you have these what we call transistors today, which are the building blocks of the semiconductor, these are fundamentally just switches. They're on and off switches. In the modern world, you know them as 0 and 1, or the machine language. So the mechanical computers were switches. The tubes were also switches, and the modern world, what we use today, are also just switches. And the history of this semiconductor is approximately 75 years old. Semiconductor means these switches or the transistors. It started around 75 years ago. Computers we have been using since around World War I. That was the mechanical or the tube-based computers. So these switches that we talked about, the difference between a transistor and those mechanical switches is that the transistor is a switch that can be controlled by another switch, which can be controlled by another switch, which can in turn be controlled by another switch. And these electronic switches, a few of them can gang up together to control a particular switch. That means if you had these, let's say you have 10 switches in your hand, you can connect them in approximately 10 million ways that you can connect 10 switches. And today we have approximately 40 billion transistors or 40 billion switches in one chip. So imagine the number of ways you can connect them together. So the switches themselves, whether they are being produced in mechanical computers or through vacuum tubes or through transistors, whether the transistors are what we call CMOS nowadays or another type of transistors, essentially these are just on and off switches. That's why even today the computer language is still 0 and 1. Is basically bunch of switches. And how you connect those switches together is what makes a chip or a computer or a small cell phone or a small toy. The ability or the way to connect these switches is what is called intellectual property. What this means is these switches that are built by the foundries in the in like the way where this actually switches get manufactured, they themselves represent just a vehicle, but to connect those switches and how to connect those switches is the actual property, intellectual property of a semiconductor company. That's why you will see that most of the powerful companies in the world that are semiconductor are not the ones that actually fabricate them or make those switches, are the ones who know how to connect those switches together. That is the world of intellectual property. So that means this IP is nothing but knowledge, right? Confucius said 2000 years ago that knowledge is the supreme. But then again, you know who else said that, right? Our Vedas also said Jnanam Paramam Balam, thousands of years ago, right? So knowledge is the most powerful or most supreme power that's not visible anywhere more powerfully than in this advanced science. Some of that you heard in the previous speaker as well. I mean, like you guys, the knowledge is the power. Now, in case of semiconductor, I am going to take you in the history a little bit, as the semiconductor has been for past 30 years. I have divided the knowledge of this producing a semiconductor chip or producing a computer chip into 7 layers, 1, 2, 3, 4, 5, 6, 7. And in these layers, of course, on the top you see is what? Profit, the money. So at the end of the day, the money guides everything else. Each of this layer actually can contain many companies. So there are many companies, thousands of companies in the world that only do part of each of the layer, not all of the layers. But there are some companies that do many of these layers together. I will give you some names that will give you a perspective. Apple, for example, has layers number 3, 4, 5, and 6, and also the 7, the most important one. This is your largest company of the world that owns 3, 4, 5, 6, 7. The company that owns all from the company that owns from 2 to 7 is Samsung, but not the most valuable company. And the one that is written there, material science, that is mostly done by governments. Nowadays not much, but mostly done by government in past. Whenever it has been done, because it requires a lot of money, first of all. The one thing I do want to make clear here is that sorry guys, I am really having jet lag. In fact, forgetting my thoughts. Pardon? Okay. Thank you so much. Yes. Yeah, well. We're going to get into deep science now. We need some fun. That's correct. That's correct. Now I come to one of the most important history in semiconductor. Though semiconductor is an area where thousands of very important people, very intelligent people, very capable people with a lot of passion have invested their lives. As a matter of fact, a lot of things that were considered great in 1950s is not, doesn't even exist. The people who actually created semiconductor did not profit a lot from it, and some profited a lot from it, probably played, of course, an important role. But one name that always comes is Gordon Moore. And all of you may have heard the name, or some of you may have heard the name, called Moore's Law. Moore was one of the most brilliant person, and he made an observation in 1967 that transistor count, the switches, number of switches on a particular chip will double every 2 years. This was actually an observation. Amazing thing is, he made this observation even before that observation really actually started happening. So this later on became Moore's Law. And Moore's law has driven the semiconductor industry for past 25, 30 years, almost 40 years. And in 40 years, we have indeed seen the effect or the effect of Moore's law, that the transistors count have doubled, or this number of switches have doubled every 2 years. And this has given rise to what you see today, the smartphone, because semiconductor is probably, chips is probably the only industry where over time the prices go down. You see in every other thing, even just because of inflation, even your rice, wheat, the prices go up. Semiconductor, the prices goes down. Either inflation is high or inflation is low. And how does that happen? Moore's law was fundamentally the reason why that happened, because the number of transistor count kept going up, and because of that we saw the computers become, or the electronics become less than $1. You can have a toy today that actually consumes a lot of these switches on one chip, and you have seen computers go from what, $100 million, probably the IBM first large computer was probably sold for $100 million. Now a toy pretty much gets sold for what, $1 or less than $1. And it has actually fueled this law has fueled the chip count, or the transistor count, the switches count to go high to the extent that we started doing software. What does software mean? Software means you give me 10,000 or 10 million of these switches, and I will use the ones that I want to use the way I want to use. That means you have to have abundance of these switches on a chip before you can start doing software, because software is basically your ability or your flexibility to be able to connect many transistors together, or use what you want and you don't use whatever you don't want. And also so basically these Moore's law I am postulating here, the Moore's law is responsible for creating the software industry, which has become now trillions of dollars, of course. And you heard all of our first half of session, basically trillions of dollars, as Ram's presentation also showed, trillions of dollars of wealth in that industry. And another thing that this has done is that you see labor became upper class. Some of them became very rich, of course, in this industry. And those are the high skilled laborers that work in semiconductor industry or in the software industry. So, and of course it created hugely profitable tech companies. Now, Moore's law also actually put the seeds of stagnation, or seeds of problems that later on happened in past 20 years in hardware industry or in semiconductor industry. Why? Because the increase in count, in transistor count, meant that a company, let me just see, hang on. So the change, the number of the increase in transistor count meant that I would be able to serve the industry and I can increase my profit. And the way this transistor count increase started happening later on was just by making changes into layer 1 and layer 2. This is called process shrink. Process shrink meant that one could increase its profit, it can gain more performance, you can lower the power consumption, and you can make smaller devices just by doing R&D into layer 1 and 2. You did not need to do the work in 3, 4, 5 or even the layer number 3, 4, 5. So what this means is that by just doing R&D, which was the job of the manufacturing companies, the semiconductor company started making all the profits. They did not need to invest money in 3, 4, and 5. That means those layers started disappearing. And when those layers started disappearing, because the profit was possible simply from just doing the layer 1 and 2 or just by the foundry or the manufacturing company itself. The investment in hardware almost all disappeared, and the software investment increased. As you can see on the right hand side, the hardware investment became just 10% of the total investment in the industry as late as 2020. This happened because of this mechanics that settled in because of this Moore's law, is that the hardware companies or the chip companies were able to make their profits without doing anything pretty much. That's why you will see that a big problem that actually really settled is that for 20 years people started believing that hardware was for free. You did not need to buy anything. Hardware should be given for free, and all of the money should be paid only for software, right? Hardware is the actual thing in real, but this is really what happened, okay? That's why in last 25 years, what we call instruction set architecture, this is a measure of new hardware creation. In past 25 years, you see only one. In first 20 years, you saw around 20 to 30 ISA created. In past 25 years, we created only once. And the layer 3 skills have completely disappeared. Only rare companies have it. One company that has that type of skill today is Apple. Okay? And most other companies have only partial skills of layer 3. And layer 2, if you try to find architects today in the world, they are counted on the numbers. So, this is all good. Everything was going well. Software is where the money is. It's very easy to create. Let's put the money in the software, right? And then process shrink. The benefits that was all happening, it all started disappearing. As you see, only the cost per chip or the cost of the of every chip when you produce go to the lower nodes, which are called these in nanometer, 130 nanometer all the way to 18 angstrom today, or 1.8 nanometer, that is Intel's. So, how am I doing with time? 10 minutes, okay. So, around 2005 time frame, the problem actually started. But in 2015 time frame, it became very obvious that by just going to the next node or just by doing research in that 1 or 2 layer or just by the manufacturing company alone, you cannot gain all those 3 benefits. So, all you could do is get one benefit, that is you could reduce cost of the chip, every chip. But to produce the chip, you needed to pay a lot of money. That means you have to pay a few $50, $100 million first, and then maybe your chip cost will reduce from $2 to $1.50. Not an economy that can work, and hence most of the companies stopped going to the next process unless you had such a huge volume that you could sell hundreds of millions of those chips in a year, right? So, the next thing that happened was even more dangerous. What happens? You are not able to make profit because you are not able to go to the next node, and you do not know how to improve your chip anymore because you have lost all of the other expertise. Profits still have to increase, and how does it increase? Through consolidation. And in past 15 years, most of the very many semiconductor companies who were actually leading innovators, some names, IBM, LSI, Avago, companies disappeared. Philips, all of Japan disappeared, completely gone in past 15 years. So, we were headed for, there was even a presentation by one of the EDA company CEO that he projected that in next 5 years, we will have only 2 semiconductor companies left in the world, okay? So, we were heading for those 2 companies to be left, means all of us to completely be jobless, and then something else happens. AI arrived. And this completely changed everything, because AI now needed everything that we did not have. We did not have the performance. AI needs performance. you do not have low power. AI needs low power. And to create that, the old method of shrinking, going to the next node, right, doesn't work. Actually, I was just a few seconds. There was a company called Bitmain. They contacted me and said they were going to this from 10 nanometer to 7 nanometer, and they think they're going to solve their problem. I said, don't even go there. It's not going to solve any of your problem. Your power consumption will not reduce, which was their biggest problem. They did not listen, and you may have heard that they actually signed up a $250 million pre-order to TSMC, and when they were in trouble, they had to pay that $250 million. They couldn't. CEO went to jail, just in China, just to let you know. The problems. People didn't realize this happened, and this is the chart that shows you that the requirement that AI has put on the semiconductor is really the term, Ram, you use, explosive. And most of the companies that have been making a lot of money from semiconductor, they actually do not have a story. And only thing that was available in the market at that time was GPU. And the name is Graphics Processing Unit. You tell me, where is AI in this? Nowhere, right? So, graphics became the vehicle for solving AI problems. If you think about it, I don't want to get into that, but it's actually a wrong thing to actually solve AI problem. However, since that was the closest thing available, we started using GPUs. Now the problem, if that was not enough, what happened? GPT arrived, or what is called generative AI arrived. Personally, we used to, within Ambient, we did talk about AI will have multiple layers of applications. GPT is just 2 layers, and our own belief is that this is going to actually become many layers. 2 layers is not enough. However, some of the data, if every person who is doing search today was to go and use ChatGPT, the world does not generate enough power to feed the computers if they were built with NVIDIA GPUs. Example number 2. If all of the users of Google, my friend here, he has come from Google, so my colleague, so he will tell you, if all of the Google users, search users, were to start using ChatGPT or generative AI within Google, all of their profits will disappear overnight. That's how much electricity bill will rise. So, we need chips, AI chips that do AI functions and consume less power. Sorry guys, so what does this mean? Generative AI, or the impact of AI, is that semiconductor needs to provide a lot more performance than we have today. GPU is not the solution, and we need it to be affordable. Recently, so I think Dubai bought 300 chips, $40,000 each, $120 million bill to build a few servers, just to give you an idea. Each server takes around 6 GPU, or 6 to 18 GPU. 300 means just one rack of server, $120 million. That's the price tag. It's not sustainable, right? Yeah, you can go use ChatGPT, that's all great, but who will pay the bills? Unless you were to invent the semiconductor. So what does it mean? If you need to build a semiconductor for AI, you must go to the drawing board, and you see what the girl is doing. 5 plus 5 is what? Right? You really got to get back to that basic. And what is that basic? Actually nothing, complicated. We have already done it in past. These 7 layers, look for the answers on those other layers. The layers that we have. So that means, now we, of course, Ambient team, bet on this particular fundamental projection that as AI progresses, it is going to need to resurrect the expertise. Thankfully, our team had worked on such chip in past, or such a project in past, and we do have the expertise that that can create AI chip that is low power, that is low cost and has high performance, all of them, which is generally considered impossible. If you go to VC community and the knowledgeable people, they will say, no, no, you cannot get all three, you can get only one, or you can get only two. Why? Because that's what we have learned in past 15, 20 years, that you cannot get all three. That's just is absolutely garbage. Anyway, because we have been able to prove so, I don't want to get into the list here, but we have invented, we have innovated in those three areas. I'm going to just take a liberty here to make, our strategy, our research, our team's overall work that we have done in 5 years is actually lined up to what I'm going to say here. I know I've heard for security guys, quantum computing is here and today, but for us who produce real things that we use in our hand, I think quantum computing is at least 40 years away. And I will be available for debate if you disagree. If you agree, then I'll be ready to discuss as well. At least 40 years away. And I think CMOS will carry the baton for next 40 years. CMOS today is at 1.8 nanometer, which is 18 angstrom. I think it will go all the way to 1 angstrom. And all of the equipment, the chemicals, the chemistry, the processing technology, the data science, all of the things that need to carry that burden to go to 1 angstrom will happen. I mean, because the demise of CMOS has been predicted at least 10 times in past. It has not happened, and I do not believe it will happen till we reach 1 angstrom. Why did I stop at 1 angstrom? Very long explanation, but I'll not get into that. There is one item do want to discuss. For past 15 years, there is one item that has been completely ignored. That is wiring on the chip. Inside the chip, we have things that get connected with each other, and this wiring has actually been ignored for past 20 years. In one of the companies I used to work for, Sun Microsystem, in 1999, we were discussing a component called dielectric constant. The whole industry has not worked on this for past 20 years. They have not even moved an inch. It was 3.2 at that time. It is 3.2 even today. This will get to 1.1, which is the dielectric constant of a vacuum. Very long explanation why that is needed, but that is needed. That will happen. Okay? One such example to give to create such a technology, what we had to do is we created a block. We call it a DGAN block. This block is able to compute an AI algorithm in 32 steps what a CPU or like a Intel chip will take 1.2 million steps to do. So we are able to do that in 32 steps. That tells you how much power we can save, how much performance we can give. And with that type of technology, we are able to produce an entire roadmap of chips which can build very small device which can be sold for $1, $2, $10, all the way to supercomputers. And we are actually actively engaged in conversation to build the large chip for one of the server companies right now. In our business strategy, we started in a place where there was no competition. If you look at the top right corner, NVIDIA dominates that market. We did not want to fight a big gorilla. So we started in an area where they could not compete with us because they have to build that technology. They have invested, I think, $300 million in conjunction with Stanford. We are lucky to be ahead. I think they will come, but not yet. So that means we have started in an area where they're not there so that we will be able to, we don't face their competition. I'm happy to say we have our first product that is shipping. Can we please help me out, Satish? Sorry. This has already gone to many customers, all outside this country, unfortunately, but hopefully we will have some here. And I think we met Naveen recently. Yeah. We have kept, unfortunately, not working dummy devices, and I'd like to explain some of them. A lot of applications just coming out of this one chip. This is the chip here, very small chip. This costs very little, and I'll show you some of the devices that we can build with this. I'll just skip the team slide for now, okay? There is a device that I want to talk about, because this is the device that started it all for me. My father had an accident, he fell, and there was nobody to attend, and we couldn't make him survive. And that's the time when I left my last company and started Ambient. That's this locket. It should be on your desk, all of, right? This is not working yet, but this locket will have our chip, and using AI, you will be able to detect if a girl is being attacked, if somebody is being kidnapped, or if my mother is having asthma attack, or if somebody falls. This device price target is $10 selling price. This should be connected to the internet. We do have a company, not inside this country, has signed up already. We have been trying to find a partner for this for past 2 years, and haven't had the luck yet. Hopefully soon. Another device I would like to show you, the camera. No, can you get that camera? This is a camera device which will run on battery. Selling price $20. You put it on the schools, on premises. It can detect if somebody is carrying a gun, somebody is carrying some other dangerous things. You can protect entire school for just $1,000, $20 each. 50 of these devices is sprinkled. So this has really become the AI dust that you would talk about. Okay, your Alexa in future will just be a pin. You will be able to say next slide or connect to this thing I was having trouble with. You'll be able to do that using just this Alexa device. The camera that I showed you will actually become this size, and you can, we have a discussion with the police department in USA, put it into their addresses, just cost $5 each. Make address, if somebody pointing gun at them, they will get a notification, they will go. Also working with an automotive company that is putting a camera like this to detect if a driver is falling asleep on the wheel. So then start playing music or tell him to just shut up and park your car, take a sleep, just like me, sorry. But so these devices already in making, some of these models on your desk. Please take a look. These are not working yet. They will be available in market very, very shortly. We are a startup. We are raising our next round. If you're interested, please do contact us offline. Sorry for the trouble in the beginning. And questions? Okay.
So with all your experience, where do you think the photonics chips come into place? Because the electrons getting hot and the chips are getting hot and they jump sometimes. Circuits are getting smaller and smaller. So where do you think the photonics chips in the space sit?
Okay, very loaded question, right? But see, photonics on and off, I am actually personally not a believer in that. The reason being that manufacturing the glass, right, the particle, this is very difficult because it's amorphous, not hard enough. So because of that, I mean, just to make a waveguide today for the networking module, so difficult, the last part actually alignment gets done by hand, you know, even today. So very difficult to increase the count. So I don't believe it will solve the problem of AI. Quantum will come before that. That's my postulation. I mean, that's my prediction.
Got it. So until then, GPU solves the cryptos problems, GPU will solve the AI problem, GPU will be the only one.
Till then, yeah.
Okay, thank you.
Yeah. Yeah.
So this is Nirupam from Hero. How we can reduce the cost, and again you gave the example of GPUs and UAE acquiring such, and again there's a horde now to pre-book all the GPUs available, and TPUs also, Google is trying with the TPU structure. What do you think India should do? You know, especially, again, we have a semiconductor thing, but we are again looking at a much higher microns. You talked about even lower, I think. So what should India be doing in that sense to secure the processing power for the AI that we will need? Because we are again looking to become an AI power. So how do we do that?
One best thing to do will be contact Ram. He will huddle people like us, bring them here, and then definitely there will be a solution. From price point of view, just to give you an idea, this is not the price that we can quote, but instead of $40,000, we are talking about that same chip with around 4 times more performance in price range of around $700. So that should give you an idea of where this type of technology is capable of building things.
Question from me, yeah?
Okay, there is coffee, looks like Ram is saying. Yes, yes. Okay, okay, please. 2 more questions Ram has allowed, so please. Anyone?
Question again, what is the, it's a system on a chip because you're talking about different applications on the same chip, so I'm assuming it's programmable in some way, or you etch the final system on a chip, right? Do you have a firmware on it, or it's just a hardware, semiconductor chip? I mean, is there a firmware, is there a layer, is there a software on it, or it's just a firmware and hardware?
No, this technology that we have created has many layers, and the top, it is actually what you would call a microprocessor. Okay. Microprocessor by definition are programmable by software.
Okay, sure.
So this is fully programmable. Even the AI algorithms are fully programmable. That means, and we very soon expect to maybe tie up with Coursera and start teaching them in right here in India. Probably
so you can make your own applications using this.
Absolutely, chip. You can do that today on this chip.
Thank you.
Yeah. But as we build other chips, we will have different configurations of what you call system on chip, where we put different components and that becomes system on chip. But the current one is more targeted for this type of small applications.
Okay, last question.
Good evening. I'm Kriti Luthra, Sustainability Manager with eValueServe. And also by profession and qualification, I'm an engineer, electrical and electronics. So my question is, nowadays that we are seeing a theme of G20 and B20 at large is ESG, decarbonization and sustainability. So, and we also talk about Vasudhaiva Kutumbakam. So I just wanted to understand when we are talking and so much advancing and going deeper into technology and chips, I had a study done a few weeks back which talked about that India is still not very strong in terms of recycling or decarbonizing of e-waste. And e-waste, when I say it, is computers, laptops, and the chips and the keyboards, which is full of chips, thousands of chips. So what is the actual physical space occupied by the chips, and is there a way of revolutionizing it? Like, do we have a proper recycling ways or reforming these chips? Because I also understand there is a lot of silver and gold in the keyboard wirings hidden, and India has not yet been able to reutilize that minerals, important minerals and elements.
So when people talk about e-waste, there are a lot of things being confused. See, the e-waste chip occupies probably less than 10%, actually less than 5% of the real estate of the computer. If you look at the full computer, the chips themselves will occupy less than maybe 5% of the area. So chips themselves are not the big problem. Also, as you said, inside there is actually gold. So, and when you break it into small pieces, chip inside is sand, is silica. So it is just like dust. So the chips themselves are not the problem. It's all the fiber or the board, PCB that we call it, that is the problem. Okay, that the current chips you see the integration as it called SoC. Like if you look at Apple M1 or M2 chips, they basically integrated a lot of things integrated into one and made it all very small. So it will cost a little bit more, but the way the chips are going, as I said, the chips are the only things, electronics only thing the prices go down, or for the same price you get more features. So this will thing that will happen over time. I personally don't worry about that. Unfortunately, a lot of what is in the media is kind of, it's like a big elephant, blind people looking at different part of it and they don't really get it, unfortunately. So experts sitting together can solve a lot of these problems. Unfortunately, this electronics has always been democratic. Nobody has cared whether my device is saving his mother's life or my mother's life. Now, geopolitics making it all just too complicated. We engineers have never been designed to be that complicated, right? But
Okay,
that's all
then,
we have the time for.
yeah,
Thank
just
you.
the last question. Here.
The permission has to come from.
I'll
Okay.
catch you later. It's no problem.
So, okay, go ahead.
No, I think it's a good tech, amazing tech. The size is small. Now we need one more thing. We need the power to drive this. And currently, all the batteries we have. I mean, if I have to use just a small chip, I need to use a battery 3 times, 4 times, 5 times this chip. So maybe you can do some innovation in the first layer to get
Yes.
some miniature batteries so that we can drive this chip and have the small power.
If I had coffee in time, I would have really started from that layer, sorry. But yes, the right place to actually innovate will be that first layer. And if ambient type companies or bunch of experts were to get the capital, then it is actually very easy, well, not easy, but it is feasible to create a new transistor that will produce that will consume lot less power consumption. See, the fundamental problem is in past 20 years, we have mostly forgotten to do R&D. We have been just making more and more money by doing very little work in semiconductor. So just put good people on the table and I think things will happen. That's my answer.
What do you think, guys?
Sorry. Sorry for all the...
Great presentation, GP. And I got one thought here. We got 2 very amazing entrepreneurs that are waiting to present here. You're going to love it. You're not going to fall asleep. I guarantee you that. But let's do this. Let's go over there, grab our cups of tea, come back in here.
Yes.
Let's make it a working chai break, okay? So we get started, okay? So let's go grab our tea. And please don't hover over there. Come right back in, and we'll get going. Thank you.
Thank you, Ram.
And also this evening we have a wonderful